We have a power equation for wind, and the power equation has V velocity in it. But that implies that we always get the same power out of a wind turbine. So what do? We use just one velocity. We use a mean velocity. Is that representative? No, the power changes all the time because it's a function of the wind speed. So we need to know, well, what is wind speed actually? Is it always one velocity that we see on the Canadian wind speed atlas? No, it actually follows a statistical distribution that we can mathematically predict. So wind speed is not constant. Now, what do I mean by statistical distribution? Well, statistical distribution, one of the famous things is talking about bell curves. Well, let's do an example for your grades on what people call a bell curve. So let's look at a distribution of grades. Let's say this is 100% and this is 50%. Well, what does the curve for grades look like? So bear with me for a minute here, and we're just talking about grades. So what does the curve for grades look like? Well, we hope that there are not a lot of students who get a grade under 50, but it does happen. We hope a lot of students are sort of in this 70 kind of range, 80 kind of range, and then there might be the odd student at 100. So this is what the distribution for grades usually looks like. They call it belling a curve, but it is not a bell-shaped curve. Bell-shaped curve looks like this. This is a mean, this is a mean distribution. And that's what we call a bell. This is a mean distribution. So a mean distribution is symmetrical on one side and the other side, and that's normally called I don't remember what that's called, but this is your mean. And then I believe this is called your distribution, this delta. So this is the mean distribution. This is not, and the mean distribution is what we often refer to as the bell. This distribution of grades is not bell-shaped. If we listen to all of the cartoons and TV and belled your grades, then that would look like, that's probably referring to going like this, so that everybody is sitting in here between 50 and 100. But what your grades usually look like is about like this. Now, I want to talk about what that curve actually means. What is on the y-axis? Well, what the y-axis is actually, this is a summary of these buckets. Oops. So what are these buckets that I'm drawing? So think about that. I drew a whole bunch of vertical buckets. What do they represent? They are buckets of data. They are quantities. So they are the number of people with a grade. So I would say number of people. So let's say I have a class of 100. Then I would say the majority of people, let's say this is 70%, majority, that this count inside this bucket is higher. Whereas over here at 100, this is like one person. And down here, less than 50, let's say you have 3 people. Okay, so this is what a Pareto chart looks like. This is called a Pareto chart. So we have to remember that word Pareto chart. That is not an XY distribution. That is not what we commonly look at as like an X, Y scatter plot, it is a representation of a Pareto. And then on top of that Pareto, so you can make that Pareto, and then on top of that Pareto, you can define a bit of math, and then you can make a formula curve. So here's a curve representing that Pareto data, and this curve would have a formula. And in terms of a mean distribution, this is a simple formula. This formula is a little bit more complex. The one for grades here is a little bit more complex, but it would have a formula. You can make a plot like that on Excel, and then you can even just click a button and it will make the formula for you. So the formula is a mathematical relationship between what's on the x-axis and on the y-axis. So why am I going on about Paretos? Well, we need to know the statistical distribution of wind speed. And wind speed actually does follow a common distribution. I can tell you your grades in my classes follow a common distribution that looks about like this. Wind speed follows a common distribution as well, but it looks different. It looks more like this. All right. And you can tell this normal distribution is different than this grades distribution that always peaks sort of over here, and which is different than this wind distribution. So now I'll leave this history in the background, and we'll talk about the distribution that looks like this. So it's simply, so this distribution is what fits the data the best. So what I'm saying is when you take buckets of wind speed, you most often, you get the most number of data samples in this wind speed, and you get the least data samples in this high speed, if this is velocity. So you get the most over here. Now the mean is going to sit around about here. And that mean is what we call average velocity. So let's take a look at a Weibull distribution from some actual data. And so here's some data. I won't say example, I'll say illustration. And I'll show you real data from 3 years. And from that real data, it Paretoed out like this. And this is the wind velocity. And that this was taken hourly. Measured hourly. And then over here we have the number of recordings. So the number of records of a certain velocity. So let's look at the velocity of 0. Let's look at this as 0. And the number of records with a velocity of 0 is actually around about 500. I'm going to make this chart go to 2,000 records. And up here in this velocity, this data, this actual data that I've got is measured in knots. And that's not really that consequential to us, but It's a way of measuring wind speed. You probably want to know the relationship between knots and meters per second. I'm just having trouble in my document here. I got into the margin of my document. Sorry about that. So 1 knot of velocity is, a knot is a common way of measuring wind speed. I think it's a nautical term. 0.52 meters per second. So you'll be more familiar with meters per second. But my point is that at around, this was around 10 knots. I'm going to make this chart go to 30 knots. Around 10 knots, you start seeing a lot of buckets of data measuring in the 10 knot range. And then, so some of them are higher, some of the velocities have more frequency, some of them have lower frequency, but there are a lot around 10. There are less closer to 0. And then around 20, there are not very many samples at all of wind speed this high. And then there's even less around 30. So the really high wind values did not get found very often in this sampling. So the samples look about something like this. So this is actual data, and of course you're wondering, well, where was that taken? I don't remember where this is taken, but it doesn't matter because wind speed typically everywhere it's studied in the world actually follows the same distribution. And this is the most common distribution that fits the data. So if I were to draw the curve representing this, it looks like this. And this curve is well known. It has a name. Just like the bell curve has a name. This is the mean distribution. This kind of shape that goes like this has a name, and it is called the Weibull distribution. All right, so Weibull distribution is the most common distribution that represents the graph that shows the buckets of samples that you have measured at every velocity. So I hope that that's a good description of why we have this Weibull distribution that represents wind. Weibull distribution has a formula. The probability distribution function as it relates to velocity is equal to a shape factor K over a scale factor A times the velocity, which is our x-axis variable again, over the scale factor A times shape factor minus 1. E, mathematically E, negative velocity over the scale factor times the shape factor. This is the equation that you would come up with if you tried to make an equation of that line. It's basically saying the probability density function of V relates to V in such a way that there are constants here, a constant in the denominator, a constant in the denominator here, a constant in the exponent here, e to the exponent, more constants with your variable, and another constant. So I don't expect you to be able to derive that because that's a mathematical situation, but that is the equation for a Weibull distribution. This is for velocities greater than 0 because the Weibull distribution is not valid in negative numbers. So here, velocity is wind speed, and K is a shape factor. And A is a scale factor. The shape factor determines shape, and the scale factor determines scale. So if A were a larger number, then it would have a much bigger scale. If A were a smaller number, the scale would be smaller. All right, let's look at the effect of K. Now I'm going to draw some Weibull distributions, but without the buckets of data. And so this is your wind speed, and let's just say meters per second because it's relative. And this is your, I'm going to say, I could rename this to say probability. Because really this axis is talking about buckets or samples, which is also a frequency or a probability. And I'm going to add some data on here. Or I'm going to give you some scale. All right, so let's put that much of a scale on it. And down here, wind speed in meters per second, I'm going to say 5, 10, 15. Ooh, that's very high wind speed, 20. Now K is your, determines the shape. Let's say we have a really high K. Well, let's do a medium K. Medium K is around about what we saw before. So a medium K is going to look, a medium K is going to look about, it's going to look about like this. Okay, not a lot of high wind speeds, mostly around 5 meters per second. So this is K equals 1.5 shape factor. Now, if it had a really high K value, then it's going to peak like this. So this is K equals 3. So this is a high K value. It's taller, skinnier. What this is really telling me is that the wind is more predictable, right? Most often around 7 meters per second. So it doesn't happen very often that you're at 0, and it doesn't happen very often that it's very fast wind. So this is kind of where I would want to build a wind turbine. So you have to compare. Is it worth it for this blue location to get some really fast speed sometimes, or is it more worth it to be in this situation where I know that I'm going to get a pretty consistent wind speed? And what you would not want is something like this. A very low K value would look like this. So this would be K need to study the wind profile. And I'm going to say, which one would you choose? Would you, let's say these all have the same mean, would you put a wind turbine where this K value is equal to 1? Would you put a wind turbine with that kind of distribution? No, because most of the time you're going to have very low wind speeds. So that's the most common distribution in wind speeds. Now, sometimes we collect wind speed data and it more resembles a different distribution called Rayleigh. So Rayleigh is almost the same. It just, this curve is slightly different. It's a different equation than the Weibull distribution. But you can tell it's not a normal distribution, and you can tell it's not the same distribution you get in your grades in the class. But it looks like the Weibull distribution, but it is actually slightly different. All right, so in the next video, I'll talk about how that affects power density, because power density obviously was only had a velocity v in it, but now you know velocity v changes over time as governed by a Weibull distribution.